Welcome to my computer network series. Today we are exploring error detection techniques. Let's explore how to use redundancy techniques like Parity, Checksum, and Cyclic Redundancy Check catch errors in the data link layer before they cause issues in the network. Moving on to the concept, when a frame travels from the sender to the receiver, bits can get corrupted because of noise or interference. Look at the example. The sender sends data 10110010, whereas the receiver has received 10100010, which means that the fourth bit is error. There are two types of errors, single bit error and burst error. If only one bit in the data is changed, that is either 0 to 1 or 1 to 0, it's called as single bit error. This is an example of single bit error. If two or more consecutive bits in the data are changed, it's called as burst error, multiple bits error. Fine. So what exactly happens at the data link layer? The sender adds some extra bits to the original data. These extra bits are called the error detection bits, or otherwise the redundancy bits. Redundancy is the most important idea here. Redundancy is added to the frame so that errors can be detected efficiently. So the original data added along with the redundancy data is transmitted. At the receiver end, the receiver checks for the error detection bits. If suppose there is no error, it accepts the frame. If suppose it finds an error, it discards the frame. So this is what is the simplest error detection that's happening between the sender and the receiver. So what are the error detection techniques that we are going to discuss? Number one is parity, number two is checksum, and number three is CRC, which stands for Cyclic Redundancy Check. Let's explore these one by one. Parity check is the most simplest technique amongst all. We are going to add one extra bit called the parity bit. And this parity bit can be either even parity or odd parity, which has to be agreed between the sender and the receiver prior. Let's see a simple example of how to add even parity. In an even parity, the total number of ones should be even. So, suppose this is the data, count number of ones. You count number of ones, there are 4 ones. It's already even. So, the parity bit added is 0. Look, the parity bit 0 is added along with the data. Now, what about odd parity? In an odd parity, the total number of ones should be odd. Suppose this is your data 10110001. Count the number of ones. There are 4 ones. It is not odd. Make the number of ones odd. So the parity bit that you add should be 1. Now the number of ones are made odd. It is 5 here. Done. So this is what is even parity and odd parity. So now what is actually happening between the sender and the receiver? The sender, along with the data, computes the parity bit, sends the data and the parity bit to the receiver. The receiver takes the data along with the parity bit, computes the parity bit, checks whether it is even or odd. If it is even parity agreed between the sender and the receiver, if it is even number of ones, accept the data or reject the data. If it is odd number of ones, odd parity agreed between the sender and the receiver, if number of ones are odd, accept or else reject. This is what is happening between the sender and the receiver. I can view this in two ways. One, longitudinal redundancy check LRC, and the other as vertical redundancy check, the VRC. Let's see small examples with LRC and VRC. Let me take a data word 10110111. At the sender, count the number of ones row wise, right? So there are 6 number of ones, which is already even. So the LRC parity bit is 0, as we have already discussed, right? So the transmitted data will be 10110111 along with 0. So this technique which we have already discussed, I call this to be the LRC, longitudinal redundancy check. Okay, so now what actually happens at the receiver end? If at the receiver end if there is no error and the receiver gets exactly the same data sent by the sender, now number of ones is 6. LRC is correct. The receiver accepts the data. Done. What if one bit has changed? Suppose the receiver has received a error data like this: 1010011110, where the fourth bit is in error. Now what happens? Receiver counts number of ones. Number of ones is 5, which is odd. So even parity has been agreed between the sender and the receiver. So since number of ones is odd, there is an error detected and the receiver is going to discard your frame. That's it. Talking about a simple example in vertical redundancy check. Look, now in vertical redundancy check, your data is arranged row wise, and for every column you calculate the column wise parity bits, right? So assuming that even parity is being agreed upon between the sender and the receiver, now you calculate the column wise parity bits. After calculating column wise parity bits, your VRC becomes 1001. This 1001 along with the data is transmitted to the receiver end. What happens at the receiver end? The same process is repeated. So this is your data along with your parity bits, and column wise parity is being computed at the receiver, and the receiver finds even number of ones, so no error is detected. So this is what is being done at the receiver end while doing VRC. Moving on to one other powerful technique, which is called as checksum. So how checksum works? It's so simple. The basic idea is this: the data is divided into fixed size words. We are going to sum all these words and takes one's complement, and that one's complement is called as the checksum. So now we have computed the checksum. What should the sender and the receiver do? Look at the picture. There is a sender where the sender divides the whole data into subunits. I assume each subunit is of size n bits. So subunit 1, 2, 3 up till k. I find out the sum of all these subunits and I find the ones complement of the sum. Now the sender transmits the data and the checksum. At the receiver end, what happens? The receiver again sums all the subunits. Look, subunit 1, 2 until subunit k along with the checksum is summed. So takes one's complement of this sum. If the one's complement is all 0, it is no error. If suppose it is not all 0, then the receiver assumes that it is error prone. Look at the example. The original data is divided into blocks and the sender sums. Don't forget to take care of the carry. And the checksum is calculated. How to calculate the checksum? Takes one's complement of the sum, that is checksum. Now the data along with the checksum is transmitted to the receiver and the receiver performs exactly the same operations. It sums all the words. Don't forget the carry. And the sum is calculated. Takes one complement of the sum. If the complement is all 0, accept the data, means there is no error. The last important concept is cyclic redundancy check, which is the most powerful technique for error detection. CRC is based on binary division. Unlike checksum, which uses addition, redundant CRC bits are appended so that the transmitted data becomes exactly divisible by a predetermined generator polynomial. What happens at the receiver? The data is again divided using the same polynomial. A zero reminder means the receiver accepts your frame, while a non-zero reminder indicates the error at the receiver. Look, there is a data and a generator polynomial. Fine, after which you have the divisor. Divide, find out the CRC. Data along with the CRC is sent to the receiver. The same process is repeated at the receiver. Data along with the CRC. Use the divisor, find out the remainder. If the remainder is 0, the receiver accepts the frame. If the remainder is not 0, the receiver rejects the frame. What is the basic working principle behind CRC? You will be given a data word of length n and a divisor of length k. You append k minus 1 zeros to the original message. Now perform binary division. The remainder of the division is equal to your CRC. Now, what is transmitted? The actual data along with the CRC is transmitted. So the code word is data with append k minus 1 zeros plus CRC. So CRC must be k minus 1 bits, very important, and the length of the code word should be n plus k minus 1 bits. How should you do this? Let me take an example. Data is 100100. Look at the generator polynomial. The generator polynomial is x cube plus x square plus 1. So convert this to a binary notation form. You have the x cube component, x square component, there is no x component, and there is a constant component. So this becomes your divisor. Now there are 4 bits in the divisor, so add 3 number of zeros here. Divide, find out the remainder. So what is transmitted? The actual data plus the remainder is transmitted. Receiver side, what is the code received? 10010000001 is received. Now use the same divisor, divide. You get the remainder as all zeros. Since the remainder is all zero, the data has received without errors. If the remainder is not zero, it means that the data has been error prone. So to summarize, VRC uses parity checks column wise. LRC does parity check row wise. Checksum is a simple technique where addition and complements of data words is done. CRC is a very powerful technique where we perform polynomial or modulo 2 division using XOR or a simple binary division. Error detection is our first line of defense in network communication. By appending redundant bits, whether through simple parity checks or checksums or advanced polynomial division via CRC, we ensure that corrupted frames are successfully caught and discarded rather than corrupting upper layer processes. Any doubts? Post it in the comment section. Thank you. Happy learning.